Okay, I just wrote a note right here. This is a exercise we're going to do later on. Okay. So let's see if we can use what we learned today and do some kind of complex mathematical problem. Okay. So what we're going to learn today is about creating functions. Actually, we have talked about functions in the past, and now we are trying to build a class of a series of functions. So you can create your own class. So inside the class, you can have multiple functions. So for example, if you have a class, it's called calculus. You want this calculus class to have the ability to do derivative and integrals. So you can define your own differential function or integral function inside this class. And when we have this, later on when you try to choose the method or function you are going to build, you are going to use this object-oriented method to call the function. So you are going to choose the name of the class, dot, and then name of the method, then you can use it. So you can say a class is like a folder of multiple functions you build. Okay? So this is a class. Now, inside the class, there are some actually predefined function names or method names that has been defined by Python. So you cannot create your own function using those names. So those names are really weird. 2 underlines, new, and then 2 underlines. 2 underlines, initialization, and then 2 underlines. And then string, and for, this is for like, I think it's equal, right? So, why does Python define those methods in those ways? Because those are some functions that are commonly used. Okay, so okay, so if you have a method inside a class called new, this method will be the first one to be called. Okay, whenever this class is being activated. Okay, and initialization is like you want to have a like initialize the entire class. So sometimes if you want to initialize some important functions or parameters inside this class, you can put it inside initialization. Okay, and some others. Usually I use these two the most. Okay, string returns a string to describe the object. Okay, so if you want to have some information that is described by a string, you can use this. Okay, so this one will tell you whether 2 objects are the same. Okay, I don't use this one too often. Anyway, let's take a look at this one. So here's one example. So if you have a class and you define this predefined the initialization function, and over here there is some variable pretty unique. It's called self. So self is like a local variable inside the class. Okay, so you can use this self. So this self is going to be inside the class. You can share this variable with your neighboring function. Okay, so over here, you know the initialization method will be run all the time. It will be at the first time when this class is being utilized, then it will run the initialization. So over here, you print out some sentence, and you will define a variable, and inside the variable, a self variable, and you can also use this object-oriented method to have some parameter inside self. So self.name becomes what you provide to Python, which is a person's name, Brian. So self is a local variable inside the class, and it has a child object. It's called name, and this object now equals to a string. Okay, so initially you will run this part. So right here, the example code define a new variable called m, and equals to the class. So now the capital M is the class. So if you say m.myFunction, so basically this is calling the second function, and say JSON. So what happened is it will print out 2 lines. First line is TA's name is Brian. Okay, the second line is new name is Jason. So the new name came from the input you provided here. Okay, and the TA's name came from the initialization. Okay, so over here you can use this m to call methods from the class. Or right here you don't really need to use m. You can directly use the full name of the class and then call my function inside. So let's try this in Python, and I will let you practice. So now let me do a side by side. Okay, so here you create a class. So maybe I try something else. I will try my math. Okay. Now I'm going to define also initialization and self. Okay. So inside the self, I want to print out a line and say delta equals to, or say the, or I just define first. Let me define delta first. So self and delta, because later on I want to solve a math problem with a parameter called delta. So I need this to be a small number. Okay, and then I want to print out. Okay, and say delta equals to if I do that, okay, let's just have that for now. And if I say n equals to my math, okay, and run the code, you can see I didn't do anything. I didn't call the function. I just defined the class as a shorter name, capital M. But when I do that, this class is being activated. So if the class is activated, I need the initialization part will be the Python will run the initialization part. And because inside this part, I create a variable called self.delta, and I print it out on the screen. So over here you can see delta equals to the number. Okay, okay, I don't need a space here. Yep, it looks better. Okay, so let me continue to create a second function. So over here, I want to define so-called f prime. Okay, and then I say self, and I need to give a number. Let's say 5. Okay. No, not 5. I should say x0. Okay, so here I'm going to. I need a way to calculate something. Let me calculate f. So let me just call func. Okay, and then maybe I don't need self. I just need x0. Okay, so evaluate some function. Over here, I'm gonna import math. I'm gonna use some function inside that as m. But if I do that, I don't want to misuse this one. So I'm gonna call this double M. Okay, my math. Okay. So it doesn't allow it. M1. I haven't finished yet. Hold on, let me continue. So over here, I should return. So let's say m dot sine function and x0. Okay. So if I do m1 dot func and say sine, for example, sine pi. Okay. And then maybe I print out this value. Okay. Hold on. I should. Oh, sorry. No, that's fine. Trying to figure out what was wrong. For text one composition argument, the 2 were given. 2 were given? Sorry. M1. Oh no, M is here. This is fine. This is correct. M sine. Trying to figure out what was wrong. Do I need to use self? Let me see. Okay, you still need to have self right here. Okay, now because I defined this inner variable, so I have to have this inner variable inside the function. But even though I didn't use it, I will use it later on. So right here, you can tell I just computed sine pi. Sine pi equals to 0, right? But numerically, Python computes as a super small number, 1.2 times 10 to the power of negative 16. This is almost 0, okay? So that's calculation of sine. Now I want to take derivative. I will show you how to do derivative. So if I say, so basically f prime. Now I know I need to put save self here. Okay. And also here, I think x0. Try not to use the same name, just x1. Okay. So f prime, so you return. How do you compute first order derivative? Basically, you will compute let me make sure I do this right. You're calling another function inside a function. Just make sure I'm doing this right. Okay, I should be able to do something like this here. So I probably will do this. You see, super dot func. Just double checking. Let's try x1. Should be not sure. Let me try it. So print m1 dot f prime, and then n dot pi divided by 2. Okay, try this. No. Not by super. This. It's not attribute. Okay. It's not by this. Then can I do this? Maybe not. Not sure. No, there's no. Oh, okay. Let's see if that's the good way. I think this may not be the best way to do it, but it works right now. Let me see. This is attribute. Okay, anyway, at least it works right now. Let me continue. So over here, I can, may not be a good way. So I just call the, or maybe I just use my map. Has to be. Okay. How about, let me see, just double checking. Okay. M1 actually better. So what's the difference? Okay, if I directly use M1, the initialization part won't be executed again. But if I say my math right here, that means every time you activate you call the class one more time, the initialization part will be run one more time. So if I do this, you will see this delta, this line is shown twice. Because over here I did it once, and over here I did it another time. So I guess it would be better if I use M1 here. Okay? So over here I'm running my f prime, right? So f prime pass the value to here, and then it pass the value to my func. So the value goes to my func, and then return back. Okay? So now I can do some math with my func. What I want to do is I want to add a delta and divide it by this value again, and the whole thing divided by delta. So it's self dot delta. Okay. So this is basically approximation of the f prime. So if you check over here, in calculus, we learned this limit delta x close to 0, f of x plus delta x minus f of x divided by delta x. This is the definition of f prime, right? Definition of f prime. So I'm doing this in computer. I plug in a value plus delta x minus the value by itself divided by the small increment delta. That gives me f prime. This is how you compute f prime. So let's see. At the end, okay. Let me use, let's think about math. This is sine, right? Sine at pi equals to 0, right? So sine prime at pi actually equals to cosine pi. So cosine pi should be -1, right? So let's see if that's -1. So if I plug in sine pi, you see the value is -1. But I never compute cosine. I never use function m. I never use math library. I truly compute the derivative of sine, or using the definition of calculus. Okay? So over here, what happened was, let me tell you what happened inside Python. Over here, first line, I initiate my math. So this part will be, Python will run this part. So I define a small value called delta using this local variable called self. So self.delta is a local parameter inside the class. Now, first I will print out function of pi. I don't want to use 3.14, so I use math, and so it helps me to get pi. And also inside the function, I use the library inside math, so I can compute sine more easily. So from here, function pi goes into here. So x0 basically equals to pi right now. So over here it will compute sine pi. The value will return back to the original line. So return back to here. So the value of sine pi returns back to here. Then I print it out. Okay, so next line I compute f prime. So basically f prime over here is going to be cosine. So basically f prime, and then my input is pi again. I plug in, so x1 equals to pi. So what does f prime do? F prime will not directly use cosine because I can change this function all the time. So if I write down cosine here, that means in the future when I change function, I need to change f prime as well. I don't want to do that. I just want to use one equation to compute f prime for all kinds of functions you have right here. That's why right here we use the approximation from the definition. So over here, plug in the function, plug in the value, basically is pi, but you need to plus a small increment, delta. So delta was created when you firstly initialize the function. So you can use the delta here. Minus the function at pi, the whole thing divided by the small increment delta. Okay, so at the end, this value will be returned back to the printout. So inside f prime, when you call m1 function, it will go to this function right here to compute whatever function you have. So if I make a change, if I change this to cosine, I only need to change f function right here and print it out. You can see cosine pi is -1. So cosine, take a derivative, is gonna be negative sine. So negative sine pi is basically 0. So you get a value very close to 0. Okay? If I do another function, for example, I comment this, I say x0 square plus or 5 times x0 squared. Okay, and over here pi, let's just f0 squared. Okay, so if I do that, x squared, and if you plug in pi, so function is basically pi squared, so it's gonna be 9 point something, right? X squared, if you take the derivative, is gonna be 2x, right? So 2x, if you plug in pi, so 2 times pi, so it's going to be 6 times 2a. So you can change any function right here, and then f prime is going to take a derivative. If one day you change the delta to a larger value, the approximation will be bad. So supposedly it's 6.28, not 38. So the accuracy of f prime really depends on how small your delta is. From the calculus, delta has to be very small, so it's close to the real derivative. So you can choose a small number like this. Then your f prime is accurate, 6.28, 2 times pi. Okay? So let's practice this. You can, if you want, you can build your own function. But I choose this example because later on, I want you to experience how to truly solve a math problem. So whatever I'm building right here can be used later on. Okay, I will give the monitor back to you, and if you have questions, you can look at the screen.
对对对。那个。就是变狗狗。对对对。所以这是整张。
Okay. Okay.
Did you get it? Did you get what I did? Let me do one more thing. I'm not going to, I'm not going to take over the screen. I will do something on over here on the top, in the front. I'm going to show you how to do f double prime. So I'm going to call this prime 2. That means second order derivative, okay? So similar to f prime, but this time you need to minus 2 times of f of x plus another term, but over here minus delta. And when you divide everything by delta, you need to divide everything by square of delta. Okay. So this means square. Okay? And then I'm gonna print out m1 dot function prime 2 means double prime at pi. So right now my function is x squared. So if you take the derivative twice, first x squared prime will be 2x. 2x prime will be 0. So supposedly I should get 0 at the end. No, not 0. 2. Should be 2. 2x prime will be 2. So at the end you see it's 2. Okay? If I try, let's say cosine. Yes, cosine is fine. If I do cosine, cosine pi is -1. Cosine prime is negative sine. So negative sine pi is 0. Is it? 0? Yeah. So negative sine prime again is going to be negative cosine. So negative cosine pi is going to be 1. So right here. So cosine pi negative 1. Take a derivative will be negative sine. Negative sine pi is 0. This is close to 0. So another derivative. So it's gonna be negative cosine. So negative cosine pi 1. Okay. So I will leave what I have right here. This is f double prime. If you need the math, if you need to know why, what I did was here, this one is f prime. And this one is f double prime. Okay? So you will increase x a little bit, minus 2 times of f of x, plus decrease x a little bit, and then plug in f, divided by delta squared. I know this is not a math course, but I hope when you program, you are programming for something technical. Okay, we are mechanical engineers. You solve a lot of math problems. I hope programming helps you to solve engineering problems. Okay, so I'll give you some time to. How about this? I will share the screen to you. Maybe you can use your cell phone to take a picture. That'll be easier. And then I will give the screen back to you. Okay, if it's too far away, you can take a picture right now. Okay, so I will give the screen back to you. Okay, so if you are done, I will show you another cool stuff. So there is something called Newton's method. I think I did this once. So I will show you again, something called Newton. Okay? Okay, so what does Newton do? Newton's method help us find the minimum point. Okay, so how do you do Newton's method? So you plug in x1 minus derivative of x, so basically f prime. function m1 dot f prime, right? Divided by f double prime. So m1 dot f double prime. That's it. So this is one time of Newton. So let's try to see what's gonna happen. So this time I'm not going to use cosine because cosine is a very nonlinear function. I will use x squared, just x squared. So I will common this and then x0 squared, x squared. And over here, keeping the pi is okay. So x squared, first derivative is going to be 2x. Another derivative is going to be 2. So what does Newton's method do? Newton's method tries to find the minimum point of x squared. So the minimum point of the x squared is actually 0. When x equals to 0, x squared is the smallest. That's what Newton's method do. So let's see. Ooh, something's wrong. Let me see. What happened? Sorry, I don't need those. Run again. Okay, so at the end, Newton's method gives me some value really small, close to 0. Okay, let's change the input to something else. For example, some number. Okay, some number, very large. Search from there. Say, it doesn't go to 0 yet because Newton's method will be accurate enough if your delta is small enough. So let me try a smaller delta. No, it doesn't. So maybe it needs explode. Let me try. Oh, still doesn't give me the smallest. It doesn't give me 0. Let me think about why. Why it doesn't give me 0? Supposedly it will. Let me try something not that crazily small. Not that crazily large. Oh. Okay. So I think numerical issue. Yeah. So when it's too large, it's not that effective. Okay, so if it's a number in hundreds, okay, that's fine. Okay. So numerically, if my input is too large, it's not easy for the f prime and the f double prime to be accurate enough. So if they are not accurate enough, Newton's method is not accurate enough. But a value like this can, you can use Newton's method find the minimum point of x squared. How about try something else? If I say x0 x divided by 3 squared. The answer is supposed to be 3. Because the minimum point is located at 3. When x equals to 3, this function equals to 0. So, yeah, you can see the answer is very close to 3. Okay? So I will let you again share the screen, let you copy what I have. I just created one more line to apply Newton's method. Okay, so over here you can see that we are what we are teaching today is actually not many to teach for today. Only how to use a class, how to utilize some predefined function names, and also how to create some of your own functions. So I want you to use this opportunity to solve a real problem. Okay. So let's get back to you. So let's try this. Okay.
出去了。
是你要考虑什么？
那我没开始。
你单来找我要，我会给你的。
那他交就好了。
对啊，你要是抄别人的，我会给你的。
我做完。
妈的，就在上多久？
Okay, I think some of you are done. Okay, let me show you another, what's the true process of optimization. So I may need to share the screen. You can take a picture. So in the Newton's method will approximate the location of the lowest point, but like I show you, sometimes it's not accurate. So usually in optimization, there is a process a while loop. So over here, I am showing you how to do the while loop for optimization. So let me explain what happened. So initially, you will say, define some value called error. So we want this error to be very small later on. And then create a number called iteration, iter, just for me to know how many times I run the while loop. Okay? So initially it's 0. So inside the while loop, when do we run the loop? When the error is large, we will run the loop. It won't stop until error is small enough. How small is small? I'm choosing 10 to the power of negative 6. So I want this error to be very small, then you can stop. So inside the while loop, you will run just like what I did, Newton. Okay, so x1 is my initial guess, initial value, which is 5. So first, when it goes to this line, this is 5. So by Newton's method, it will give you a return, some new value. It's a new position. Over here, you are going to compare the difference between x2 and x1. So you can use absolute value between of x2 minus x1. So absolute of x2 minus 1 is your new error. So if you already reach to the lowest point, your new solution x2 and the previous solution x1 should be very close, because this is already the smallest position. Then your error becomes so small. But maybe sometimes it's not small enough. So we want to run the second loop if error is not small enough. So for the second loop, over here, I will replace the initial guess by the new solution. So I say x2 equals to x1. And then my iteration number increased by 1. Then we will go back to the first line of the while loop. If the error is not small enough, the process will repeat until one day my x2 is very close to x1. Supposedly, that is the position with your smallest function value. And then you will stop. Over here, before I stop this function, I will print out how many iterations has been utilized. So it will show you how many iterations it run. It run the while loop. And at the end, return the final value of x2. Okay? So let me show you on the right hand side. This time I chose a nonlinear function. It's actually x minus 3 to the power of 4. So fourth order. Again, this function equals to 0 when x equals to 3. If I only use Newton's method once, just like the earlier example, it will not give me the right answer. The right answer is 3. But one trial of this Newton method gives me 4.3. It's not 3 yet. So from the while loop, actually it took this code to iterate 36 times. At the end, it found 3, close to 3. Okay. If I want even greater accuracy, I can increase this error. I can increase, for example, 10 to the power of 8. But of course, you need a greater accuracy for delta as well. So maybe 2 more zeros. So now we have 2.994. Can we get 3? Because I require greater accuracy for the error, and I use greater accuracy for delta, so my f prime and f double prime approximations are more accurate. So earlier it was 2.994, now it's 2.59. It's closer to 3. Okay? So this is one example to truly solve an engineering problem. finding the minimum point of x minus 3 to the power of 4 using Newton's method. Okay? You can take a picture and then you can try it. Okay, I'll give you some time to take a picture. Okay, now you try it.
四，在玩这样，
那你切回去一下。
妈的给你玩。
Okay. Did you all get it? Okay, so this is a Newton's method for one-dimensional problem. Actually, I want to show you how to do two-dimensional problem today. I'm not sure if I should do it or not. Let me see. Let me just double check before I do this. Okay. Okay. So I'm going to. If you're done, I'm going to show you. I'm gonna share the screen, and I'm going to do the 2D problem. It's more complex. So I'm not sure if you can complete everything today, but I want to show you. So let me share the screen. So you can at least take a look at how I do it. But before I do that, I need to make sure I can do inverse of a matrix. So I need NumPy. Okay. So import. NumPy as n. Okay, I need this. Then I will need to define my function. I need to transform all the functions into a two-dimensional problem. So here I'm going to just say x1 and x2. So over here you can actually have two variables. So here is x1 squared is enough. So maybe x2 minus 5 squared. So it's now it's a two-dimensional problem. Since it's a two-dimensional, when I do f prime, f double prime, I need to treat it as two-dimensional function. So for all the functions, now is a two-dimensional problem. So over here, this is x2 here. x2. Okay? So two-dimensional. Since this two-dimensional, there's going to be partial derivative. So I need a second line. Also f prime, but now I don't want to call it f prime anymore. It's it should be something called df dx1. Okay, and this should be df dx2. Derivative over with respect to x1 and x2. They should be separate. Okay, and then I will show you what's the difference. So the difference is when you do partial derivative, you plus the delta on x1 for df over dx1. And when you have the increment of delta on x2, you are doing df over dx2. Okay? So this is actually a vector cogradient. So I'm going to define something called gradient. For the gradient, I also need the values. So it's a vector. It has to be a vector. So the vector, I'm going to formulate a NumPy array. It's a vector. So return a NumPy array. Okay. So it's going to look like, make sure I should be doing this. Okay. Oh, just. Okay. So vertical array. So the first one would be this. Second one would be this. I'm not sure if it is going to be a vertical one. So let me, now I have function. So let me just try different values, just 1 and 2, okay? And I will test derivatives, also 1 and 2. Okay, and then second order derivative, first order derivative, and then I want to show the gradient. Okay. Here, the gradient. Just want to make sure this is correct. So I may need to just comment this part because everything is different now. But I need those later on. Okay, so here. Just let me make sure this is correct. df. Function. NumPy is an issue. Can I? Sorry, I should say M1. Here, okay. Run the code in. I don't need self. Okay. Yeah. So now it's if I call this. So the gradient is an array of floating numbers 2 by 1. Okay. So it's a vector. Okay, it's a vector. It's a vertical vector. Okay. Now I will. I need to make sure I can do dot product or matrix multiplication. Python NumPy matrix multiplication. Oh, matrix multiply. Okay, good. I need those. Otherwise, I cannot do the rest. So good. So far, so good. I have a gradient already. Now I need a second order derivative. So I'm going to open this. So it's a very complex matrix. So it's going to be df dx. I'm gonna say call this 1 1. Okay. And I need these. I need this. I'm gonna call this 1 2. 1 2, and then I need another one called 2 2. Okay, I will tell you what are those on the board later on. So 1 1 1 2 and 2 2 right here. The what matters the most. First one is actually 1 1. But I need to have x2 here. X2 here. Okay? Now, let me copy the whole thing. Copy the whole thing and then paste it here. Because it's gonna be the same, but the increment goes to x2. Decrement goes to x2. Okay? Now the the troublesome part is this term. This one, I need also x2. Every term has x2, but increment on x2 and x1 both minus. I need 2 of those. Minus increment on x1 and then increment on x2 and then plus itself plus the original place. That's the other term right here. Now I need to create a matrix cohesion. Okay? Self x1 and x2. What is Hessian? It's gonna be a NumPy array, but this time the df the 1 1 term, and then let me just double check if I program this right. The NumPy matrix. Okay, comma here. Okay, so the 1 1 term and then the 1 2 term. Over here, the 1 2 term again, and then the 2 2 term. So over here, the 2 2 term. Okay, that's Hessian. Let me see if I get it right. Hessian equals to m1 dot Hessian. Yes. And okay, here 1 and 2, and then print out Hessian. Run the code. Okay, something's wrong. Let me see where. Oh, let me see where. What's the problem? D, this is a D. This is a gradient after the gradient, and then return right here. Okay. Let's see what the problem is. I saw the problem. I should not have this multiply sign here. That's okay, good. So now I have a matrix 2, 0, 0, and 2. Is it right? Yes, it's right. It's a second order problem. So I just successfully got the Hessian. Let me check if my gradient is right. Gradient should be 2x1 minus 3. 2x1 minus 3. So 2 times x1 minus 3. So this should be 1 plug in. So negative 2 times negative 4. Yes. So the other one should be 2, negative 3 times negative 6. Yes, correct. So yes, we're almost done. Now I will show you how to do Newton. Newton will be a vector as well. So it's more complex. I should be define initial vector, let's say call x0. So it's a array, and x1 here, and then x2 here. So initially, when you put in two numbers, I create it as an array. Now I will. Oh, I don't need this. No. I just need to say, oh yes, I need this. Sorry, I need this. Here will be x0 minus, over here, this should be inverse of the Hessian, inverse. So NumPy function, let me double check. Inverse, okay, here. NumPy linear algebra inverse, okay. NumPy linear algebra, linear algorithm dot inverse. Okay, great. And then I will have inverse of Hessian. And then I need to do multiply. Maybe I will cut it into two lines. So I'm gonna call it Hessian inverse. Okay, Hessian inverse is this guy. Okay, so here I can just say HI. And then I need to do matrix multiplication. Matrix multiplication, I already Google it. It's gonna be, let me see. It's called matrix multiply. Okay, so NumPy matrix multiply. Okay, so use the Hessian inverse multiply. Just double checking. Should be something like that. This is top product. Okay, A times C. Okay. Do I need to say dot shape? Maybe not. I think this should be fine. Okay, now I'm going to put in the M1 dot the gradient. If I'm right, this should work. Okay, so let's double check. I don't need this line anymore. I will need to check over here 1 and 2. Newton, yes. So if I'm right, the answer should be 1 and should be 3 and 5. 3 and 5. So So let me just say x1 equals to this. And then just print out x1. Okay. Did I say 3 and 5? Yes. Yes. 3 and 5, right? So initially, I put in 1 and 2. This Newton equation gives me 3 and 5 because that's where the answer is. Okay, but it's not accurate enough. I want to do optimization process again. So here, add x2 right here, everything almost the same, but right here you will do Newton's method x1 and x2. So I cannot call this x1 and x2 anymore. I'm gonna, and in return it's going to be NumPy array. So I'm gonna call this y. So y is a NumPy array. So when I calculate this difference, I need to compute something called norm. So Python NumPy norm. Okay, norm. Norm just a vector. Okay, so great. NumPy linear algorithm dot norm. Okay, NumPy is so powerful; it has everything. So now I need y. Can I do this? Let me try. Y minus the linear array here. Okay, I'm not sure if this is working. Once I have this, I will say I will replace. Let me see how do I call this gradient. The first one. Gradient. Gradient. First one. Oh, okay. I can. How do I? Let me see. Not sure. I'm not sure. How about gradient 1 and 1? No, 1 and 1. No. 0. Yes, I should do this. So x1 equals to y, because it's an array, so the first one and the value inside. And x2 equals to the array, second one and the content inside. Okay, that should work. So in return you will just return y. So over here I will say y equals to M1 optimization 1 and 2. Print out the result y. Okay, boom. So do you think it's more accurate? It took 3 iterations. Yes, it is. You probably cannot tell. Let me try to enlarge, for example, 4th order right here. So you will see, initially Newton's method gives me result 1.6 and 5. But the while loop operates 63 iterations, 63 while loops, at the end 3 and 5. So from here you can tell it's more accurate. So what happened? I should show you so many math. What happened? I will use this board right here. So I may need to just turn off the screen. Okay. So what happened was, if you are curious in linear algebra, This is Newton's method for 2D problem. So for 1D problem, actually, what we did in the earlier example, we said you can do this to find the minimum point. So earlier we have some value, we guess, minus the first order derivative of f over second order derivative of f. Basically f prime over f double prime. This is Newton's method. It will give you the lowest point of f. But it's not accurate enough. That's why we did this iteratively multiple times. Then at the end, if this value equals to this, that means you cannot find even lower value. So that's the optimal. That's the position with lowest function value. But this math can only be used for one variable, so only one x. How about two-dimensional, basically x1 and x2? How do you solve it? This is how you solve it. So everything becomes vectors. You cannot have math dividing a vector. Math doesn't work like that. You can only divide something by one value. You cannot divide something by a vector. So for linear algebra, there is something called inverse. So if you do inverse, it's just like dividing that whatever that's inside the matrix. So over here, there is something called gradient. This is gradient. Gradient. Okay? So gradient is a vector that keeps the first order derivatives, but it's partial derivative. It's df over dx1 and also df over dx2. And this matrix is cohesion. Okay? So this is a matrix that keeps all the second order derivatives, all the possible kinds. This is the second order derivative with respect to x1. This is second order derivative with respect to x1 and x2. This is with respect to x2 and x3. This is the one with respect to x2. Okay? So Hessian, all the second order derivatives. What we want to do is your original x minus, also minus, gradient over Hessian. But you cannot directly have divided by the matrix. So you can use inverse. And over here there is a dot product. So it's a Hessian inverse dot product with your gradient. That's what you are going to do. That's what I did. So inside the Hessian and gradient, there are partial derivatives. My code basically did all the partial derivatives. Here's the one that we did at the beginning. Partial derivative, basically df dx1. You will have this increment delta on x. And for the partial derivative with respect to x2, you have your delta increment on x2. That's the only difference. Okay? Second order derivatives are more complex. Okay, this is the first one. So you have delta here, you have delta here. Okay? For the other one, this is the other one. This is second order derivative with respect to x2. You will have increment on x2 and decrement on x2. Okay? The most complex one is this one. The one with x1 and x2 at the same time. So you have to have increment on x1 and x2 at the same time. Okay, minus the one with increment on x, minus the one with increment on y, plus the function value at its original location. Okay, so once you have those, put them into Bayesian, put them into gradient, do the final equation right here. That's Newton's method. Okay? Don't worry if you have no idea what happened, because you're only freshmen, right? You may not learn this anywhere. However, if you learn this, you can practice linear algebra and then learn how you can program this in Python. So since you know a little bit about this already, let me go over my code again so you can have a comparison. So let's review what happened. Now I have second or two-dimensional problems. All my functions has two inputs, x1 and x2. And I'm trying to do partial derivative with respect to x1 and x2. For the first one, I have increment of delta on x1. For the second one, I have increment of delta on x2. So I formulate them into array, NumPy array, because I want to use some of the nice matrix calculation methods in NumPy. That's why I form them into NumPy array. So from outside, when I call gradient, it actually goes to this part first. And inside the gradient, it's formulating a NumPy array. And inside the NumPy array, it will call the estimation of derivative for me. So this is the first one, this is the second one. It forms the array right here. This one. This one is the gradient. So my line 14 is trying to do this. Okay? Now, why did I say 1, 1, 1, 2, and 2, 2? Basically, it's talking about the position of the Bayesian matrix. This one is the 1, 1. This is the 1, 2. This is the 2, 2. Why didn't I do the 2, 1? Because the 2, 1 is the same as 1, 2. I don't need to do it twice. Okay? So I did second order derivatives of 1, 1, 1, 2, and 2, 2. Over here for the first one, you have increment of delta on x1, decrement of delta on x1. Okay? Hold on. Okay. Now for the 1, 2, it's the most complex one. You have an increment of delta on x1, increment of delta on x2, and then increment of delta on x1, increment of delta on x2, and also at the plus the function value at the original position. Okay? For this one, the last one, second order derivative with respect to x2. So you have increment on x2, decrement on x2. Okay? At the end, when I use Bayesian, I formulate them into a NumPy array. So this is the first row, second row. Okay? Now, for Newton, when I provide x1 and x2, I need them to be formulated into a NumPy array. That's why I have this x0 equals to a NumPy array of x1 and x2. And then I need to compute inverse. So use NumPy, linear algorithm, inverse, and then Bayesian, x1 and x2. In return, the equation I have right there for Newton's method, it's a dot product between inverse Bayesian and the gradient. Okay? So that gives me returning an array of the new position. So from if I do the while loop, this time, every time I run the Newton in return, it's a NumPy array. So when I compute the error, this NumPy array has to minus the other NumPy array, which is the earlier design. So I'm pretty sure the output of Newton is a NumPy array. So when I do minus, I need to make sure I'm also minusing another NumPy array from the current point. So norm, what is norm? What is norm? Norm computes the, let me write down here. So this is so-called norm. Okay, so basically square root of A1 square plus B1 square. So norm, this is called norm. Norm computes the length of a vector. Oh, let's just say A2, not B1, A2. Okay? So when I try to compute the error, what I did was a vector of y minus a vector of x. X is my earlier design, y is my new design. I ask them to subtract with each other, and I compute the length of that vector, the difference vector. So that's why I use norm. Okay? So from here you can tell, if you are doing programming, you need to be good in math as well. Math is a fundamental knowledge you need. Programming is just one way for you to calculate math. Okay? So over here, the error is the norm of y minus x. At the end, because I need to go back to my second while loop, for my Newton's code, I didn't for the input, I didn't assign the input as array. My input was just two values. So I need to take the value out of the array of y. So right here you can see my y is an array of in the size of 2 by 1, right? 2 by 1. So if you want to take the value, if you say y0, y0 is also an array, basically the first one. How about y and 1? Is the second component inside the y array. So it's an array inside another array. If you want to truly take the value out, you need to do this. So you truly take the value out. You just want value. I don't want the array anymore. So you have to do something like this. Okay? So x1, x2, I truly take the value out. Iteration number plus 1. Yeah, that's it. Okay, let's run the code in. Okay. If I also change this to the fourth order, okay, 65 iteration. True answer, 3 and 5. If x1 equals to 3, x2 equals to 5, the function equals to 0. Basically, is the smallest possible value you can have. Okay, so I will share this with you maybe directly from a file. So the TA will send the file to you. You still have a lot of time for the class. Don't just directly copy from my file. Try to type it by yourself. When you type by yourself, you have some memory about the coding. And if you made a mistake, you can compare it with mine, so you know, oh, I should be careful on this and that. So TA, please come here, send the file to them. So for today, please try to run my code. Either it's mine or you type it by yourself. We cannot tell. But before you go, try my code. It's a two-dimensional Newton's method. Okay? So please do it. Any questions? If you have questions about optimization, linear algebra, you need to take some other courses, not from here, or you can come to me. Hey, professor, just teach me this. No problem. Maybe in the future. But the purpose here is to show you how you truly can program a math problem solving by Python. Okay. So, if no questions, I will let you to practice.